In this video, we're going to continue talking about oxidation and reduction, followed by balancing equations. When it comes to oxidation and reduction, we have already observed how there is a change in oxidation number for separate elements in a chemical reaction. So at this time, I would like you to practice by doing the problems on letter A, C, and D. One of the things that we can observe in these reactions is that at times we observe these large digits in front of the components in a chemical reaction. And those are called coefficients. Now, why are they necessary? In chemistry, whenever we have a chemical change or a chemical reaction, we must write it in a balanced form. In a balanced chemical equation, no atoms are lost or gained, and the number of atoms in the reactants are going to equal the number of atoms that we have in the product. The reason why this needs to be respected is because this is based on the law of conservation of mass. And in the law of conservation of mass, it actually particularly describes how matter cannot be created out of thin air and destroyed into thin air. There cannot be, in an ideal case, a change in the total mass of a reaction. So that's why the mass of the products equals the mass of the reactants. To illustrate this, we can observe here the following reaction. We have solid silver reacting with solid sulfur, making silver sulfide. If we look at the screens for the analytical balances, we can see that we have the measurement in grams of each of the components of the reactions. And when those amounts are added, it actually equals the grams that we find of the product. This is in an ideal case. This is the expectation in chemical reactions. So how do we guarantee this? Well, overall, we're going to see how this digit of 2 needs to be placed in this reaction in order to balance the number of atoms that we have overall. When we examine the chemical reactions for the components of this reaction, we can see that at first we may have just silver, sulfur, and in the chemical formula for silver sulfide, we see that there's a 2 next to silver. So in order to balance the number of atoms, then this large digit of 2 in front of silver needs to be placed in order to balance the reaction. And then on each side of this chemical equation, we're going to have 2 atoms of silver, 1 of sulfur, 2 atoms of silver, 1 of sulfur. Balance equations, remember that they are coming from the idea that we need to respect specifically the law of conservation of mass. What you observe here specifically is going to be some guidelines of how we write balance equations. As I mentioned, these are just guidelines. In order to master balancing equations, what we need to do is practice as much as we can. The main thing that I want to point out of all the information in this slide is specifically that we only change the coefficients in a balanced chemical equation. We never change the subscripts, because if we change the subscripts, then we're changing the chemical formulas, and that is not allowed. Let's actually practice balancing equations. In this problem from the textbook, we have different equations, and we need to balance them specifically by looking at the number of atoms and then putting coefficients. I'm going to first do letter B. This is my equation on letter B. I have oxygen gas reacting with phosphorus in solid form. And then I'm making tetraphosphorus dicoxide in solid form. So when I'm trying to balance a reaction, I need to write how many atoms I have of each of the components in the reactant in the product. This table is going to look very similar to the table that we generated for oxidation number, but understand that this is in terms of balancing the number of atoms in a reaction. So in this reaction, I have oxygen and I have phosphorus. I have the number of atoms in the reactant and the number of atoms in the product. I can observe that when it comes to oxygen, I have 2 atoms in the reactant, 4 atoms of phosphorus in the reactant. When I examine the product, I have 4 atoms of phosphorus in the product, and I have 10 atoms of oxygen in the product. Now, looking at this, it appears that my phosphorus is balanced, while my oxygen is not balanced. So I need to find a coefficient that when I multiply by the subscript is going to give me the number of atoms that will be equal to the one that we see in the product. So for this reaction specifically, we must put a coefficient of 5 in front of oxygen. And when I take 5 times 2, that means that my oxygens will go to 10 atoms. And now I have the same number of atoms in reactants and products for my oxygen and my phosphorus. As you can observe, I didn't place a coefficient on P4 or P4010, but they do have coefficients. The coefficients that they have will be a value of 1. So I want you to take a moment and balance reaction D. In this course, you also need to be able to take reactions that have been given in words and you need to balance them. So as you observe in reaction 1, we have the following reaction. Solid potassium oxide plus liquid water make solid potassium hydroxide. Let's do that problem together. First, I'm going to write the chemical formulas of all my components in my reaction. So potassium oxide has a chemical formula of K2O. Water has, and this is in solid form, let me include that. Liquid water means that H2O in liquid form is present. I place the arrow. The product of this reaction is potassium hydroxide in solid form, and this is KOH in solid form. So if I make my table to understand what specifically I have here, I have potassium, oxygen, and hydrogen, and in the reactant versus the product, this is the atom count. In the reactant, I have 2 potassiums. In the reactant, I have 2 oxygens. In the reactant, I have 2 hydrogens. In the product, I have 1 of each atom. To balance this reaction, what I need to do is place a coefficient of 2 in front of KOH. Remember that we don't change the subscript. We put a coefficient in front of the whole chemical formula for the atoms that we're trying to balance. We don't do it before the element that we're trying to balance. We do it before the whole chemical formula. So taking that into consideration, potassium goes to 2, oxygen goes to 2, hydrogen goes to 2. And now on each side of this reaction, I have 2 atoms of potassium, 2 atoms of oxygen, and 2 atoms of hydrogen. Take a moment and determine what is the balanced chemical reaction for reaction 3, where we have solid silver oxide decomposing to solid silver and oxygen gas.